Our next talk is by Dino Bektesevic. Sorry, Dino, if I'm mispronouncing your last name.
It's close enough.
Oh, okay, thank you. And you're going to be talking about running Rubin LSST science from AWS. So welcome.
All right, thank you. So I'm going to first tell you a bit what VRC Rubin Observatory is, then what their science pipelines are and what they do. And then I'm going to talk a bit about how we run them on AWS and why. I'm going to try to keep it short, but if you have any questions, feel free to post it in chat. So VRC Rubin Observatory is an 8-meter telescope currently being built in Chile, on which the legacy survey of space and time, or LSST sky survey, will be conducted on. But the goal of this project is to conduct a 10-year-long survey of the night sky that will image the entire visible southern hemisphere every 3 to 4 nights. And the 10 years, the survey estimates it will deliver 200 petabytes of images and other data products, hoping to address questions about the structure and evolution of our universe. And for astronomers, this is an order of magnitude more data than we're usually really accustomed to dealing with, right? For example, Pan-STARRS survey that ran from 2010 onwards boasts itself as having released the largest volume of astronomical data to date, but that's still about only 2 petabytes of data in total, right? So the data volume produced by Rubin is kind of a novelty, and the question of how to process and share that data received a lot of focus within the astronomical community. The project itself will reduce the data in 2 computing facilities, one being, so this is a bit older slide, but one was NCSA in Illinois. That seems to be will change soon enough, and one will be in France, the CCIN2P3 data facility, right? And these data facilities will give 10% of their compute resources and offer them as shared compute resources for the users, right? And while that's a lot of compute resources, and while it's true that primary focus for many astronomers will be catalogs, which are smaller, right? Given these data sizes, the allocated resources are not really a one-size-fits-all solution, right? So we started asking ourselves in the Dirac Institute, where I'm a fellow, could we build a system that would allow users to process data at the sizes of Rubin, and could they use that to speed up their science, and could this be affordable and easy to use, and could it support users that want to do a custom analysis of the data that will not be provided by Rubin, right? And thinking about it, and this need for scalability and shareability with the code, but maintaining low cost, we were naturally led to a cloud compute model. So with that, decided to give it a go, right? And we picked Rubin LSST science pipelines to do it because we wanted to leverage the existing state-of-the-art functionality in astronomical data reduction that's part of these pipelines. And the science pipelines essentially enable processing of astronomical data from a single exposure to joint calibration of multiple exposures. But in essence, all they do is they take a raw data, they take a raw exposure that's freshly read out of the CCD, and they calibrate, characterize it, and also create some kind of a catalog that has all of the objects detected on it and all of their measurements, right? To give you an overview of the science pipelines and sort of explain the infrastructure designs we made later on, I want to show you this diagram, right? The very obvious purpose of science pipelines is to build and run pipelines that result in science, right? But this includes running science algorithms, whether image or catalog processing one, to produce some measurements and other data products, right? These science algorithms are represented by tasks, for example, astrometry task or photometry tasks. And these tasks, it says Python objects and input, but them themselves do not do any input-output operations, right? They do define required configuration of parameter configurations of these science algorithms, right? These tasks, they can chain into a pipeline. A pipeline is described by directed acyclic graph, a DAG called a quantum graph. Each quantum, a node in the graph, is a task applied to a data set. So now here we have an identifier for which data set we want to run on, right? But all of the I/O in this pipeline, in this chain, is abstracted to an interface known as the data butler, right? The purpose of the butler is to isolate the end user from file organization, file types, and related file access mechanisms by exposing data sets as Python objects, right? And they're referred to, the data sets are referred to that by their unique IDs or set of identifying references, which are then resolved through a registry, which is usually an SQL database, and a data store, which is usually, let's say, a POSIX file system, right? And since the data butler interfaces all of the I/O for every task in the science pipelines. Adding appropriate functionality just automatically makes this stack capable of running using cloud environment services, right? So we opted to do this in Amazon Web Services or AWS. We used S3 simple storage service for the data store, and we, for the registry, used Postgres SQL. We used the AWS Relational Database Service, or RDS, to launch Postgres databases in AWS. We used the Elastic Compute Cloud Service, or EC2, to get compute resources. And in effect, what this gets us is we can define and build a quantum graph on our local compute resources or in the compute resources in the cloud, and launch processing that will take and output all of its data requirements into these persisting services like S3 and RDS, right? And that's already pretty cool because there's already a huge collection of commonly used tasks in astronomy, right? On top of which users can write their own tasks, and the science pipelines themselves support a variety of different instruments, not just Rubin, right? But what it doesn't get you is any way of scaling in the cloud. So to scale in the cloud, we kind of need something extra, right? So to do that, we use Pegasus and HD Condor, right? We use HD Condor to distribute and execute the workflows, and we use Pegasus to organize and distribute our workflow execution, right? We produce a quantum graph using the Rubin science pipelines, and then we convert it into an abstract workflow using the Pegasus API, right? This abstract workflow is then in the planning stage converted in a set of stage in, executable, and stage out scripts, and a DAG, an executable DAG that's readable by HD Condor DAGman, and then it's submitted and executed on HD Condor compute pool, right? The added benefit of using both Condor and Pegasus is that we didn't need to write the whole. We have a quantum graph, and we can just kind of directly convert it to Pegasus using Pegasus API, and we could skip having to write our own DAGman conversion scripts, kind of a deal, right? Additionally, HD Condor gives us additional functionality in the cloud, like dynamic resource allocation through its HD Condor Annex module, which can run a compute pool in the cloud, right? So to give you a brief overview of how this basic infrastructure looks like, user would acquire a node in which they would log in. From that node, they could acquire some kind of a compute pool, whether the more classical, EC2 type of persistent compute, or some kind of a spot fleet compute resources with an elastic load balancing service attached to it, etc. They would allocate their compute pool from their head node, build their quantum graph, convert it to a Pegasus abstract graph, and submit the workflow, right? And after the workflow would complete, the instances in the compute pool would be automatically deallocated by Condor Annex, or they could be deallocated if they were idle for too long. And the user could still access all of the data he needs or they need from the head node by instantiating a butler, right? User administration in this most basic approach, right? Each user gets their own head node. In essence, their Condor central manager and schedule, and would have to manage their own clusters. User administration would still be possible, right? But spending limits and privileges allowed or denied through the AWS Identity and Access Management Service, right? But it's not the best if you're thinking about running clusters for a bunch of people. So the question is, could a more centralized architecture be possible? And that's, of course, I believe the answer is yes. The setup should be possible. It's not still well tested because my academia keeps getting in the way. Instead of having a central manager node, a head node for each user, they would have a submit node, which would essentially run the scheduler, and there would be a central persistent central manager node through which you could additionally manage and control your compute resource pool. The other interesting bit is that the following work, which I was described on running on AWS, Rubin Observatory tried to execute it on GCE. The code changes to go from AWS to GCE were minimal because Google Cloud runs this cloud storage interoperability service that can nearly seamlessly translate requests from AWS 3 service into their GC counterparts. What is different in this architecture is GC services that were used, right, compared to AWS. And in October last year, Rubin announced that they will run their Rubin interim data facility, where they will process data in the initial stages of the survey for the CCA first 2 years or so on Google Cloud. This work was led mainly by Xin Fang, which is with us today on this workshop. And if you want to know more where Rubin wants to go in the cloud, definitely talk to her or watch her talk. The YouTube link is on the bottom, right? So this is more of how we develop our infrastructure and how it works. But how does the end user experience with the workflow look like? In idealized conditions, it should be a pretty simple three-step process, right? Users define these science pipelines using essentially YAML files containing all of the tasks they want to run, potentially some additional parameters that those and configuration parameters that those tasks take. They build their quantum graph using a pipe task, which is also a tool provided with the Rubin Science pipelines. And then they have to convert this convert the quantum graph into Pegasus DAX. There's a pre-built script we offer, but it has some baked-in resources and requirements for these jobs. If users want, they can change these, or they can write their own scripts as they please, as their workflow requires. Right? These extra steps so far are required because much of the Rubin middleware and science pipelines, workflow execution, etc., all of that code is still under active development, and there's no internal support for Pegasus from within Rubin science pipelines quite yet. I'm not quite sure when that might be the case and who will have to implement that, because Rubin has been experimenting a lot with different workflow management systems, so we'll have to see. So we ran some basic diagnostic tests for basic diagnostic purposes on a tract of a hyper-supreme CAM data set. It's about 2% of nightly volume, about 11% in the number of nightly observations. It's about 20,000 jobs, about 0.2 terabytes of input data, about 3 terabytes of output data. And we figured out that resolving bottlenecks, mainly almost always related to EBS volume, input-output congestion on the worker nodes, can yield up to 50% decrease in the time it takes to execute a workflow, and consequently a similar decrease in total cost. So that's very interesting. We found that properly configuring PostgreSQL registry is very important, because RDS will not do that for you. Other things like scaling, it's important when scaling, it's important to watch out for staging and how you handle your staging. HeadNode is not a good staging guy. Spending 5 minutes setting up a basic static stage in and dynamic stage out sites is always a good idea. And cutting down on log production really helped us out a lot, right? Interestingly, we find that cost for these runs was approximately constant, within like 7% for different tests we ran. This is expected because the cost of more powerful instances in the cloud is offset by reduction in total wall time required to run them, which means that when the cluster is oversubscribed, increasing the number of workers or selecting more powerful EC2 instances will decrease the wall time but keep the cost constant. And that's a very exciting prospect to think about, right? Why spend a week if you can get it done in an hour and pay the same? We attempted to construct some kind of a cost comparison. The data has a large variance, so these cost comparisons are not set in stone, but we find that the cost on the cloud compute resources only is between $600,000 and $900,000 United States dollars for data release production workflows that Rubin should run yearly, right? This does not include long-term recovery costs, but it is comparable to Rubin on-premise compute resource deployment, which is estimated to be around $700,000, right? For 100 instances, data is a bit over the place because the data set we used wasn't big enough, so don't look at that. Interestingly, this one test is very nice. It shows if you have a workload that can be run on spot instances, you should, because you can get another 4-time reduction in cost. The problem with spot instances, AWS can give you a 2-minute notice and take them back whenever they want. So it does require fault-tolerant software. So what's next, I guess, is the last. We're trying to land on a stable demo that can keep up with the stable branch of the latest science pipelines developments. This is challenging because their code allows for backbreaking changes, so it's a bit of a like Sisyphus type work, but it's getting there. We have Packer and Terraform scripts that deploy the infrastructure in AWS. We want to build a demo using tools astronomers are familiar with, which means you better notebooks, and for that we need more integration, both with HD Condor, Condor Annex commands, and Pegasus, let's say, service dashboard would be nice. You know, just a button to open the new web page and see how your workflow is going. Cost saving is still a big deal, so that's something that needs attention, especially the data store. Never saw in the log. There's no caching, no staging, no tiered storage, which all just makes it very pricey. And I won't spend too much time on the wall of text. I'm sorry, there's a wall of text. I think the last slide that we were asked to do, I don't know if I'm the best person to be asked. My problems are usually related to misinterpretation of what able to run on cloud providers means for different packages. For a lot of packages, that really means implementing some kind of a minimal support for certain services and then abusing that service to do things the service wasn't quite designed to do, instead of implementing functionality for appropriate services that are designed to do that functionality, right? So many workarounds in packages just include using S3 storage as a shared volume or as a way to share common credential and authentication information instead of just supporting, let's say, IAM service on AWS or some other service on GC, et cetera, right? Most of the problems, therefore, are not very Pegasus related, to be honestly. It has not brought any downsides to my projects, perhaps having to understand and navigate a sea of confusing configuration parameters. The workflow, the kinds of workflows you can run and test from Rubin are already, they have their own DAG generating machine that essentially is good because it can assume all of the things it needs to assume because it knows what kinds of workflows it runs. So all we do is translate that. Some points listed here, like better CWL support. I learned today there is a tool, conversion script. I had some experience with Pegasus 5.0 API when I was trying to do that integration steps. Some of it left me a bit confused, having to go back and read the code because I couldn't quite find the docs. I'm happy to hear there is extensive documentation. Hope we can figure out what I've been missing later today. The example I listed is the Stampede Statistics DB, which was a bit of a hard to wrap your head around. I wanted to use it to do some statistics analysis that I just couldn't get from Pegasus Statistics CLI tool, because a lot of the time cluster jobs don't provide you with atomic enough details on execution stuff, as atomic as I would like, or perhaps I don't know how to make it provide that atomic statistics that I would like. The log handling point isn't quite necessarily a Pegasus problem, but it's a pain point over log preservation accumulation in shared nothing environments in general that I've kept running into. It kind of ties into, overall post-workflow analysis and troubleshooting can be complicated because the default idea of how to handle logs is so shared everything centric. So all the logs are always files. There's no easy way to avoid that, and that means that you kind of have to centralize them at some point, and that just means that there's a lot of latency when transferring those logs, and that latency really cuts down on your CPU utilization percentage, and maximizing that percentage leads to the fastest execution of the workflow. So we found that clustering these jobs and just to kick the log handling to the end of these jobs is a big deal, because you don't waste that much time transferring the logs. Somebody earlier today made a comparison how much it costs for a cheap job to run on Pegasus compared to just directly, and that's kind of what you're dealing out, what you have to deal with these log transfer stuff. Ability to write the DAG after a partial execution would be nice. I either don't know how to do it or never done it successfully, and it's an opinion shared by people also from Rubin. that would like to see more workflow-oriented tools, or would like to learn more about workflow-oriented tools, how to manage multiple workflows at the same time, etc., are all things they would enjoy. Okay, that is it. I kind of lost track of time. I hope I didn't go too far.
Two quick questions. One, we will be on the condo side will be very interested to hear the scenarios and the semantics of the rewriting, and to see it has been always a challenge of what does it mean, how does it relate to the other one, and things like that. So I would be very interested in understanding from you an example of how you would like to rewrite. The other one, which is more of a question, is to what extent the network costs play a role in your workload? Is that an important factor, moving data, especially out of the cloud, or that's negligible?
Right. So as I said in the last slide, the data store really didn't get a lot of love. There's no tiered storage, no staging, no things like that. Data transfer in and out of the cloud would be a significant expense for a project as big as Rubin. It wouldn't be horrible for somebody running, let's say, a Rubin Night or something in terabytes. It wouldn't be horrible. There are options that allow you to hook up your infrastructure directly so that your infrastructure can look as if it's already part of AWS services, which would probably be the best way to go when you have petabyte size data sets.
So I may send you, we have some experience of running large scale bursts into the cloud and of IceCube that have some interesting network cost information that you may find useful if you have workload where moving data out is non-negligible.
Yeah, I would love to see those. I do believe if you want to download everything, that would be a problem. Maybe I'm underestimating or how much these costs would be for like a single shot workflow. So
Eva is the editor of a journal publication that has the paper. So between Eva and myself, we'll send you a copy.
Yes, I'm happy to share it, and thank you for your comments, Meron, and Dino. Thank you so much for your presentation and your feedback. It's very valuable. I appreciate the fact I'm hearing the message that our analysis and monitoring tools need work, and so we'll look for that to improve. As Meron pointed out, it'd be good to know how you want to rewrite DAG so we can support that, and so it's great that you're giving us that feedback, and we'll follow on in more detail to make sure that we address these issues. And Wendy is keeping track of everything, and we
I need to jump in with some answers. So I'll take a minute. So I think Dino, for using the Stampede statistics and workflow stats, it was never meant to be a user-facing Python API to use. We do provide a REST-based Python API for monitoring purposes, which dashboard uses to build up its state. So that would be the right thing to interface with. And that is the reason why we don't bundle the Python code in pip packages, which we don't want our users interfacing with. So I think that addresses that particular question.